Assalamualaikum and hello. It's me again, Madam Fauza here to guide you in our course for TMP3413 or TME3413 Software Engineering Laboratory. Our lecture for today is on product implementation, lecture 8. So in this chapter, we'll describe the implementation process. We'll start by discussing design completion criteria, the implementation standard, the implementation strategy, and reviews of the inspections. Then we follow the steps of IMP 1 and IMP1, IMP1 and IMPN scripts, to describe the TSP implementation process. Before starting the implementations, check to see whether you have truly completed the high-level design. For large systems, high-level design often requires several stages. At the first level, you subdivide the system into subsystem, and then component, or the modules. At the first, while doing this, you should follow the design script 1 and or the design script N process, which described in chapter or lecture 7. At the end, you should have the external specification for each subsystem, the component, the module, and should also have the detailed design of the highest level logic for the system. So if the system are reasonably large, repeat the high level design process, this time for each of subsystem and or the component. Again, you should end up with the external specification for the subsystem component and the detail of the highest level logic of each one. It's depending again on the size of the system. You might even continue this process through several more iterations. At some point, you will end up with the external specification for the subsystem component and the detailed design of the highest level logic of each one. When you move to that is when you move from the high level design to the implementation design, to implementation design. So at this point we'll end up with external specification of the system lowest level atomic module. With the truly large system, the successive system level might be the system, the subsystem, the product, component, and as well as the module. So this is the structure of in a system level up till the module. So you will see a triangle shape actually. You have one system, perhaps 2 or 3 subsystem. Then you have products, maybe more than like 5 or 10 products. Then you have several 10s, 20 components. Then you have few modules. So this is how a large system been divided from system, subsystem, product, component, and up till the module. You continue the iterative design process until you have produced the external specification for these truly basic system elements. So these elements actually are small enough to implement directly, and the sizes okay, should generally be about roughly 150 to or fewer, okay, line of code. Okay. Although this module, okay, may contain even lower level objects or routines, okay, these subordinates routine, okay, either are relatively small, okay, have already been developed, reusable parts, or are available, okay, the library functions. It may require a substantial effort to reach this lowest level specification, okay, but until you you are not ready to start implementation and should continue repeating, okay, the design, okay, script 1 or design script n, okay, scripts, okay. Also with a large system, you sometimes must implement some product elements before you can finish the designing to design others. Okay? So this is not generally a problem unless you are required to complete all the design before starting any of the new implementations. Okay? Although development contrasts, okay, occasionally, okay, requires such look-step processes, okay, it is usually a mistake. Okay, truly. So the reason is that design is a highly irregular process, okay, and in true understanding often requires more thorough analysis and even implementation of some areas before you can start to design, the others. With a large enough development team you have there, okay, perhaps in after you graduate and then you've been assigned to a bigger, okay, or larger development team, you should start, okay, the implementation, okay, by implementing any of the component as soon as they have completed, okay, their external specifications. Yeah, although it is risky to start implementation in any part, okay, or to lay the system before you have defined all of the highest level specification, you can just try to minimize such problem by breaking a larger system into a component, then try to implementing the component when their external specification are complete and have been inspected. Okay? And if a short development cycle is important, this approach can save quite a great deal of time. Okay? A great deal can be said about the importance of a standard, okay? But the actual job of developing and using standards should not take a great deal of time. So there's a few minutes spent defining standard early in the project can save a lot of time later. First, agree as a team on the standard you need and then ask one or two team members to develop the draft. Okay? And then, okay, the team uh, can productivity product pro- produced, okay, at least the discuss and discuss the draft and agree on content of the specific standard, okay, they will use, okay, that the team agrees on the draft, okay, and agree on the content of specific standard, okay, they're going to use, and the quality process manager, okay, or the quality manager and process manager can lead the team on the activity, okay, standard activities, okay, in the implementation standard, okay, add to an extent, okay, during the design phase. And so, okay, you can see the following slides we discuss on the standard issues. Okay, we have standard review, okay, naming interface and message standards, coding standards, size standards, okay, defect standards, defect preventions, okay, And although this defect prevention is not generally considered a standard issue, okay, it is closely related to the defect standards, and so okay, we'll discuss it here. So when you are reviewing proposed standard, okay, for a standard review here, so when you are reviewing proposed standard, okay, be pragmatic. So if a proposed standard look as if it will work, use it and then improve it after you have some experience. Yeah, some experience with it. Don't ever try to produce a perfect standard at the first time. So you could easily waste, okay, a great deal of time, okay, debating proposal in the abstract. Okay, so you will produce better standards in less time if you start with a reasonable draft, okay, and then update them after you have tried using them. Okay. So review the name, interface, message standards, okay, developed during the design phase to ensure that they are still, okay, appropriate and are being properly used. And also don't forget to check that the list of reusable routines is complete and that all the team members are using it. Okay. Next, okay, what you need to do is in a standard review, okay, you review all the name glossaries, okay, to ensure that everyone in your teams, okay, members, okay, is using the same name for the same item, and that all the system-wide names are recorded in the glossaries, okay, like classes or the functions, the modules names, or they are related, and make sure they are similar, so everybody using the same names. So check the component and the sub element names, okay, and review, okay, the shared variable parameters, okay, and the file names for consistency. Okay. So usually these are taken into account by a process and quality manager, okay, in terms of the name consistency. So also check the standard interface, okay, and messages to ensure that all the internal and external system interfaces and messages have been defined, have been recorded in the glossary, and are known and used by all the team members. Okay, if you plan to use the same language that you use in personal software process course, okay, you can probably use the same uh, coding standard, okay, the same coding standard. Okay, make sure, however, okay, that the entire team agrees to use the same standard. Okay, so the coding standard, if you are using the C++, or everybody's using C++, or PHP, or even JavaScript, so everybody need to say mutual agreement on with the others that you'll be using the same coding standard. So make sure, however, a common coding standard ensures that all the team code look much the same and also facilitates the code sharing among the team members. Yeah, so this consistency will make code inspection easier, quicker, and more effective. So a well constructed coding standard also defines, okay, the commenting practice. So comments, which means for each of the files code, okay, program files, okay, in the header, okay, code files, you put your comments on, okay, what's the title of the name of the file code, okay, file program, okay, who have developed it, created it, and what are the functions of each of the program, okay, what are the features of the program, what will the program do, okay, etc. So this program commenting practices. So this is a part of coding practice. Okay, good commenting practice, okay, span speed code review and make, okay, program easier to enhance in subsequent development cycle. A common coding standard also facilitates the code sharing among team members. Okay, so when a program looks like code you have written, and when it uses the same conventions as well as commenting practices, you are much more likely to consider using it in your program. So such reuse can often save a great deal of design and as well as the implementation time. So ease your job, so save time, save quite a great deal, in the design and implementation. For requirements, you can use counts of either the text pages or even the numbered paragraphs, or even the shells. Shell statement used in the US. Shell is, I didn't include shell here. Shell, SHALLS. Shell statements used in the US government and some industrial procurements. Define the actions that the plant product are supposed to perform. A shell statement is generally used for each desired function. So the simplest measures of high-level design are counts of template pages, as well text lines or use cases even. So as you know, the use case specification actually are scenario cases, text-based scenarios. So for a detailed design, pseudocode test line are probably also adequate. And for a small program, you should use the line of code estimation. Estimate. You can use the actual line of code count. Use the actual to measure the size of the detailed design product. So the line of code depends on how big or how small your program or your system will be. So in addition to line of code, most product produce several types of products. Most project produce several types of products. Examples are documents such as the SRS, software requirement specification, and SDS, software design specification. In the TSP, we suggest that you use the page count. Use the page count to measure the document size. Following are some of the product elements that might need the size measures, especially document size page counts. We have the requirements such as SRS, a high level design, SDS, detailed design, screen and report, databases, messages, and even the test scripts and test material if you're using team software process. Measuring the remaining items is harder if your team is implementing a relatively small product in 1 or 2 semester course. You probably do not need to consider any size measures beyond text pages and as well as line of code. Even if you feel such measures are needed, they will probably not be useful for this project unless you have historical data on these measures. If you wait to gather this data for future product, do so, but don't spend a lot of project time doing it. Concentrate on building this product. If you still want additional measures, consider 2 questions. First question, does the time spent on this product type represent a significant part of the project work? If it does not, there will be little or no project benefit from measuring it. So the project work involved is probably too small to justify a size-based estimate and plan. Because of the principal reason you want size measures is to help to estimate and track the work. There is no need for size-based estimates when the development effort on any product type is a small part of the total job. Okay? Estimate the amount of time, okay, that you expect this work to take. Assuming that a product type represents a significant amount of work, you need size measures that correlate with the time required to develop the product. If you can devise such a measure, it will likely be adequate. If you can't, your only choice is to use a count of product elements as a simple size proxy. With the screen, for example, you are not likely to find a simple measure that correlates with development time. Okay? In this case, use screen count. Okay? Can do as well, and historical data on the average time to develop a screen. With a reasonable amount of data, okay, you use the same procedure used for object line of code. Okay, divide the screen data into categories. Okay. Some screen might take an average amount of development time, okay, whereas other might take very small, okay, large, okay, or even very large categories. The method used in PSP is to divide this data. Okay, with a reasonable amount of data, okay, you could use the same procedure used for object line of code. Okay, divide the screen data into categories. Okay, some screens might take an average amount of development time, okay, whereas other might take very small, large, or even very large amount of time. So the method used, okay, in PSP is to divide this data into a very small, okay, a small, okay, medium, okay, large, and very large categories. Okay, then subdivide your historical data into these categories and produce the average development time for each of the category. So with even more data, you could subdivide the product data into type such as data entry, okay, menu selection, okay, and so on. Okay, in planning, you then estimate how many screens, for example, okay, which is required, and you judge how many fall into each of these 5 categories. Okay, you can use the same approach with any other such measures. Okay. To see how to estimate size and use size data in this way, okay, you can refer to Discipline for Software Engineering book, okay, in chapter 4, okay, and 5, okay, by Humphrey. Okay, the standard PSP defects type should be adequate for your needs. Okay, the PSP, okay, however, does not discuss defects in test material. Okay, here, okay, in TSP, rather than add any new defect types, treat the test material as one or more component. List all the test materials defects against this component, and please don't count them against, okay, the product. Okay. Before you create any new defect type, okay, you can consider, okay, the following points, okay, for the defect types. Okay, first, okay, there's an almost infinite variety of ways to define defect types. Okay, you and your teammates could spend hours, okay, debating the types, okay, you prefer. Okay, although you might produce a superb standard, it probably not materially affect your project performance. Okay, second, okay, the reason to categorize defects into types, okay, is to help analyze and improve the development process. Although the defect type will help you to categorize a large volume of defect data, you must examine reports on specific defects, okay, to improve the process. Okay, this common way to do this. The common way to do this is to first analyze your data to identify the key types. Okay, for an individual defect type, okay, say function defects of type 80, for example, look in more detail at specific type 80, okay, defect report to see which types cause the most problem. When you identify a key problem area, say off by one errors, okay, determine how to find such error in design and code reviews. Although you could possibly break type 80 defect into multiple subtypes, it is exceedingly hard to do. So the reason is that you will almost always have an, we say, other category that invariably, okay, contain the most cases. Okay. Third, okay, here we have a defect type standard, okay, which are useful only if they are small. Okay, when one of the graduate students who work as a PSP course assistant was writing a thesis on defect type, he thought that the 10 PSP defect, okay, 10 PSP defect types were inadequate, so he devised a new 6-page standard. So the other student found the standard unusable. The more types in a standard, the more errors, okay, you will make selecting defect types, and the more time, okay, will take to categorize and record each of the defect. So this suggests that if you have enough defect data to demonstrate the need for a new data, okay, if you are having quite a lot of defect data, then you need to create a new type. So many people make the mistake of confusing defect causes with defect type. Okay, the more type, okay, for incomplete, the more with incomplete, the more which is call it the ones type for incomplete requirements, like for example poor application knowledge, misunderstanding of the design, okay, or inexperience in terms of the language use. Okay, there are not defect types, okay, rather they are defect causes. For example, most requirements errors would, if not corrected early, okay, result in a functional defect in final product. So such defects are injected in requirements phase and are generally caused by poorly defined uh, requirements. Okay, the defects type, however, are generally, okay, which are categorized into the data. Okay, number 70, okay, functions, okay, the type 80, and system, okay, which is type of 90. So in understanding of defect causes can help in defect prevention. Unfortunately, okay, categorizing defect causes is hard. So you can gather data on more than, like for example, 3,000 defects, and categorize everyone in terms of both the defect type and the cause. But however, find the cause category to be of any value, to devise effective preventive action. Okay, you need to go back and at least look at a specific defect report to understand the problems and then to figure out how to prevent them. So the problem here is one of, okay, generally, okay, which is to limit the number of cause type. They must be very general, okay, which is the general cause. and if you could, you wouldn't need, okay, the defect type. Yeah. There are four categories of defect preventions, okay, which has been categorized, okay, which is educations, okay, communications, transcriptions, and as well as oversight. Okay, for education, okay, you need to learn more on in terms of the language use, okay, the communication, the environment, and as well as the application. Okay, meanwhile, for the communication, okay, you need to fix, okay, the process. Okay, for instruction, use a better tools, a better software, okay, and for the oversight, okay, refine your process and use, okay, better method. Although there are many ways to use defect causal analysis in defect prevention, okay, they've been found that the following approach is very helpful, such as number one, okay, pick the defect type that seem to be causal the most trouble, okay, where you prioritize, okay, the most troubled, okay, defects, okay, this defect many, okay, waste the most test time, so be hardest to diagnose and fix, or otherwise be most annoying. Yeah? And then second most useful approach is to examine a number of defects of this type, okay, to identify particular defect causes and decide which one to address. Okay? Then when you see a defect you think you can prevent, make a process change to prevent it. So this kind of defect prevention is quite similar with risk management as well. You identify the risk, how you mitigate the risk, and how you handle the risk. Okay? And for the fourth most helpful defect preventions is assuming. Okay? You're assuming this action is effective. Start looking for the next defect category and handle it, okay, the same way. So these are the most helpful approach, okay, for a defect prevention. Okay, like in my case, okay, I initially had the most trouble with relatively quite a simple defect type. Okay, for example, I often failed, okay, to initialize variable. I solved this problem by changing my coding standard to initialize every variable when I first declare it. I also consistently, okay, reinitialize every variable at the beginning of every, okay, routines, okay, unless its value was needed. So in addition, I've updated my code review checklist to ensure that I actually followed this standard. So these are action resolved, okay, my problem with uninitialized variable. Okay, so the key defect prevention is to look for ways, okay, to change what you do in order to prevent the defect. Then incorporate this change in your process. Okay, next you track your performance to see how this change work. If the defect type persists, okay, figure out why the previous change didn't work and adjust the process again. When you know the cause of defects, note in the comment space, okay, especially in the log D, okay, log defect form, okay, in TSPI. If you mix defect types and defect causes in the same standard, however, your data will be unusable. So the reason is that the same defect types could show up in several different places. This will prevent you from ranking defect types by frequently, and that is principal reason for getting defect data in the first place. Okay. in design, okay, start with the big picture and you can work down into details. Okay, with reviews, okay, however, consider starting with the detail, okay, workout, okay, detail workout, and working up to the big picture. Okay, when reviewing a component, okay, for example, okay, you will encounter called the functions, okay, or subordinate object. Unless you know what this function do, you must examine, okay, each one to make sure that it does what your program expect. Okay, and the strategy, okay, which I have found most efficient is to review from the bottom up. Okay, like for example, first review all the lowest level objects that have no subordinate parts. When you are sure that these atomic object perform according to their external specification, move to the next level. Okay, then when you encounter this object in the next higher in the higher level reviews, you can really rely on them and need not review them again. Okay? So to follow this bottom-up strategy, also implement the lowest level object first, then move up to higher level. Okay, this is generally the quickest way to identify problem with the lowest level object specification. Okay, which is by finding this specification problem early, you can manage and fix them before they are widely implemented. So this practice can save, okay, quite a lot of amount of testing and rework time, because the lowest level atomic object, okay, the smallest level, are easily to reuse, and as well a bottom-up implementation strategy also which facilitates the reuse strategy. Okay. So for the implementation IMP scripts, okay, IMP1, okay, implementation 1 scripts, and as well as the IMPN, okay, scripts are shown in the table 8.1, okay, and as well as table 8.2, okay, the textbook, and in the following slide. Okay, for IMP1, okay, implementation script 1, okay, it's the initial product implementation. Okay, meanwhile for implementation N, okay, it's actually the implementing subsequent, okay, enhancement, okay, of the cycle. Okay, so IMP1 is for first cycle, okay, and N cycle for the subsequent, okay, enhancement of the cycle. So to meet IMP first cycle entry criteria, okay, you need to complete the development strategy and plan, okay, and then you need to complete the review and updated SRS, okay, and SDS specification. Okay, then you need to define and document the coding standard, okay, copies of routine, functional specification list, name glossary, and all the other standard theme which has been adopted and developed. Okay. So these are the template of script implementations, okay, for IMP1 and IMPN. Okay, as you see, there's a purpose, entry criteria, general, all the 12 steps, okay, which consists of activity. First activity, okay, is the implementation process overview, implementation planning, task allocation. Okay, the fourth one is detailed design. Fifth is unit test plan. Sixth is the test development. 7th is the detailed design inspection. 8 is code. 9 is the code inspection. 10th is the unit test. 11 is the component quality review, and lastly 12 is the component release. After you have fulfilled all the steps and activities, 12 activities altogether, okay, then the exit criteria, okay, when it's to complete inspected configuration and control component, okay, and then completed the forms for the design and code inspection, okay, unit test plan and support material. You have update your some P, okay, some Q, some S, log D and log T form, and you update the project notebook. Okay, and in end implementation, okay, which means cycle 2 and above, okay, subsequent implementation, okay, they are the same way as in first cycle. Okay. So you can refer to this IMP1 and IPN template in the ELIP, okay, the full view, okay, of this IMP scripts. In the implementation planning, okay, the first steps is to review work, okay, to be done, and make sure that all the tasks are assigned to the various team members. Okay, the engineer who designed each module or routine is probably the most knowledgeable person, okay, because some engineers are better implementer than others. Okay? However, different assignment could make sense. Okay? And one approach is to have some engineers, okay, to concentrate on design and others specialize in implementation. So the key is to consider the interests and as well as the abilities, okay, of each engineer in making this assignment. Making this assignment, and if necessary the team leader can help, okay, the team to make this assignment as well. So after the tasks have been assigned, okay, so each engineer plan his or her implementation work, okay, for those tasks that are expected to take only at least a few hours. A simple time estimate is usually adequate. For a large job, for example, such as implementing a program object or module, okay, you should make a simple PSP-like plan using some P and some Q forms. Okay, for a substantial non-programming tasks, make a plan using form, call it some task. Okay. Then after you have before that, okay, assuming that you already have a line of code, okay, LOC estimates for each component, module and object, and that you have a personal productivity data, the planning work should not take very long. After you have made the plan, update your tasks in schedule form, okay, to reflect the newer level of planning, okay, and then you produce a new earn value plan. So also have the planning manager to update this team plan as well. So at this point you are ready to develop the detailed design, okay, for the program modules you plan to implement. Okay, although there are several ways, okay, to proceed at this point, many engineers find, okay, it is most efficient to carry one program, okay, all the way from the detailed design, okay, through the unit test before starting the detailed design of the next program. So in many cases, okay, however, the design of several programs are so closely related that they should be designed at the same time, okay, in any event, be guided by the specific case, okay, and just follow, okay, the design strategy that makes the most sense, okay, in your case. Okay. So the next step is to conduct, okay, the personal design review of each modules or the object. Okay, so in this review, okay, do more just than to scan design with a checklist. Yeah, and check the loops and all the complex logic with trace table or the state machine analysis. So this is the continuation from the detailed design, okay, review. Okay, you conduct the personal design review, okay, of each modules, okay, or the object. Okay, then you scan design with checklist, okay, check the loop and all the complex logic with trace table and as well as the machine analysis. And in the task development, okay, after fixing problem found in the review, you can develop any specific unit test code facilities, because the test development usually finds more design problem than either the design inspection or the unit testing. It is important to do this test development before the detailed design, inspection. So the test development work, shows should have followed the test plan and should include the checks of all the logic decisions, the logic decisions, the logic path, the loop stepping, and as well as the terminations conditions. It should check all these variables, all these parameters, at least at the nominal values, at the upper and lower limits, the outer, the outside of these limits, and last, make sure that the program behaves properly under all, the error conditions. So in particularly, wherever a human action is called for, test for every possible type of error. This in detail design inspections, following the test development, let the quality process manager and as well the process manager leads you and one or more teammates through the detailed design inspection. Although such a simple inspection need not involve a quality manager, but you should enter the inspection data on INS form, and inspection form, and the major defect in log D, log defect. Also give copies of completed inspection INS form to the quality, and as well as the process manager and to the team leader for inclusions to be included in the project notebook. So regardless of how you do this inspection, make sure that at least one engineer completes the trace table, the execution table, or state machines analysis for every loop or state machine structure in the program. So one way to do this is to meet with the inspection team and decide who will do each kind of analysis for each part of the design. If you decide to do both state machine and trace table analysis of the same code segment, have two different engineers do this analysis. So this approach maximizes the likelihood of finding the error. For code and code review, Okay, following the design inspection, okay, code the module. Okay, then before you personally review it, look at your defect history and judge how many defects you have likely to have injected during the coding. Okay, one approach is to note the number of defects that you have typically inject per hour of the coding. So also determine, okay, number of defects, okay, let's say per kilo line of code. Okay? And when you have a sense for your maximum and minimum historical defect rates, you can arrive at a good estimates of the upper and as well as the lower, okay, ranges of the number of defects in the program. Then set a target to find this number of defects in the code review. In code review, continue from the previous slide. Okay, to guide the code review, it is also a good idea to set a time target. Okay, I suggest a minimum of at least 50%, okay, and preferable perhaps 75%, okay, of the time, okay, that you could spend coding a program. Okay, so instead, because a single reading of the source program will take much less than this amount of time. So keep going, okay, hack over the program until you have used all this planning time. Instead of looking at the code the same way every time, however, look for different things each time. Okay, check for name consistency one time, okay, and then initialization, punctuations, okay, equals, okay, equals, and then pointers, calling sequences, okay, which includes. There are plenty of things to look for. Just make sure to use your checklist as a guide. Okay, refer to the textbook. Okay, so as long as you are finding defects, keep looking even if you take more time than planned. If you can find enough defects in review, ask another engineer to review your code before you compile it. And then you can proceed with program compilation. Okay. Code inspections. Okay, after compilation, okay, you can try to compare your design, okay, your design review, okay, and code, okay, code review, yeah, so the team in terms of the team quality plan, okay, and also check the defects, okay, level and as well as defect rates. If your data indicate that you have a problem, or if you are not sure what the data mean, review your result, okay, with the quality and process manager. Okay, and the way is to tell whether program quality is reasonably good, yeah, is to use the quality criteria. Yeah, like for example, okay, the time spent. Okay, first, the time spent in design should be greater than the coding time. Okay, and second, the time spent in design review should be greater than 50% of the design time. Third, yeah, the time spent in code review should be greater than 50% of the coding time, and preferable greater than 70%. So the fifth, you found at least twice as many defects in the code review as you did in compiling it. Yeah? Six, okay, you found more than 3 defects, okay, per review hour. Okay, per review hour, okay, at least 3 defects. Then last one, okay, your review rate was less than 200 line of code per hour. So these are the we call so-called the program quality, being assessed. So after this quality check, use the quality assessment results, to guide the code inspections. So if your program quality looks good, and if you and your reviewers okay, have been consistently around at least 70%, have only one other engineer review the code. So if a program quality is poor, or your and then the other program which yield have been much less than 70%, so ask the quality or the process manager to conduct, okay, a code, we call it a code inspection, using 2 or even more reviewers here. So the poorer the program quality and the lower the yields, the more reviewers are really needed in this case. So if a program appears to have a quality problem, let's say, okay, have one or more engineer, okay, to have another review before you fix, okay, the known defects. So use engineers who have not already reviewed the program, and don't tell them which defect you, okay, and the other have already found. So when they are finished, check the review data and re-estimate the yields using the methods, okay, which have been specified. Yeah, again, okay, if they find many defects that no one previously found, do another review in the same way. Keep doing this review until every defect have been found by at least 2 engineers until you run out of the reviewer. So these are the quality criteria, okay, that have been mentioned earlier. So based on table 5.3, okay, the program quality, okay, criteria, okay, the time spent design, okay, must be greater than the coding time. The time spent in design review should be greater than 50%, okay, of the design time. The time spent in code review should be greater than 50%, or at least greater than 75%, okay, and you found at least twice as many defects in code, okay, when you compile, okay, you found more than 3 defects in review hours, okay, review rate was less than 200 line of code. So these are all the criteria to consider a very good quality program, okay. In code topic on code inspection, so after the quality check, so use the quality assessment result to guide the code inspections. Okay, first, okay, if a program quality looks good, and if you and the reviewer yield have been consistently around at least 70%, have only one other engineer review the code. And second, okay, it's consider the quality assessment is good. Okay, if the program quality is poor, or it's your and the other engineer personnel yield have been much less, okay, then 70%, ask the quality and process manager to continue, okay, to conduct the code inspection using 2 or more reviewers. Yeah, so the poorer the program quality, okay, the lower the yields, so the more reviewers are needed. Okay, so if a program appear to have a quality problem, have one homogeneous, do another review before you fix the known defects. So use engineer who have not already reviewed the program, okay, to fix the defects. So for in unit tests, okay, after the code inspections, the next step is to run the unit test. Okay, use the test material that have been developed and follow the test plan, okay, prepared during the detailed, okay, design. So following the code inspection and unit tests, okay, have the quality or the process manager review the component data to determine whether component quality is good enough for inclusion in the baseline system. Okay, here, okay, you can see the criteria are the ones that the team established, okay, is actually in the quality plan. Okay, and the quality plan, which covers the defect levels such as the defect ratios, process times, as well as the time ratios. So if a component have a quality problem in any have a quality problem in any of these areas, such as the defects ratios, defects level, times and ratios, time ratios, okay, the team should discuss the situation and decide what to do. So the choices are to put the component into the system baseline, okay, and to do more design or code reviews, inspection, okay, or to have another engineer rework, okay, rework the component before the integration. Okay. So although re-inspection or rework would take a few hours of engineer time, it's generally saved the entire team several days or even weeks, okay, of integration system test time. Okay. So the objective of this component quality review is to make sure that every program logical segment is analyzed at least once, okay, with the execution table of the trace table. Okay. So these are the example of the TSP quality plan, okay, from some Q, okay, a summary of the quality. Objective of this component quality review is to make sure that every program logical segment is analyzed at least once with an execution table or a trace table, okay? And also for every program segment that has state behavior, okay, ensure that it is checked at least once with a state machine analysis. Okay, and when a program logic is particularly complex, or if the program has many defects, okay, have two or more engineers to perform the same check. Also, when doing different analysis at the same time, use different engineers. So after in the complete component release, okay, after the completed component has passed the quality review, give it to the support manager to enter into the system baseline. Okay, so these are the last activities, okay, in the implementation scripts. Yeah, okay, this 12th, okay, activity. Okay. Then in the exit criteria, okay, need to complete, okay, the following must have in order to complete this implementation phase, okay, where, okay, you have completed, okay, reviewed and inspected all the components, okay, then the components entered into a configurations management system. Okay, you have completed the inspection as well as log D, okay, the log defects form for the design inspections, code inspection as well as re-inspections. Okay, you have the updated the SUMS, okay, summary of size, summary of quality form for the system and all its component parts, unit test plan and the support material. Okay, you have size, time and defect data, okay, been updated as well. So an updated project notebook. Okay, as a summary, the principal steps in implementation process are the implementation planning, detailed design, okay, detailed design inspection, coding, code inspection, okay, unit testing, component quality review, and component release. These implementation standards are also developed to add, okay, to and extend the standard defined in the design phase. Okay, so the implementation strategy should be consistent with the design strategy. Okay, you should implement it roughly, okay, the same order that you have designed it. Okay, in doing so, okay, you consider, okay, like for example the testing, reuse, okay, reviews and reinspection. Okay. So So if you have any question, you can just drop in, okay, to elib, okay, and ask me through email. Okay.